steady-state heat transfer concepts. So we're going to be looking at how heat actually moves through stuff like pipes and wires. And, we're going to find out why your gut feeling in engineering, well, it might just be wrong sometimes. Okay, first up, think about bottlenecks. When heat flows, it hits these barriers, right? We call them thermal resistances. Now, in a system with a bunch of layers, like a pipe with fluid inside and air outside, there's almost always one single resistance that's way, way bigger than the others. Usually it's the convection on the outside. And if that one's huge, well, messing with the other smaller resistances, like the pipe wall itself, it does basically nothing. Second, and this one's kind of wild, adding insulation doesn't always, insulate. Sometimes it can actually make you lose more heat. How? Well, if the insulation layer is too thin, it just adds more surface area for heat to escape from. There's this thing called the critical radius. If your insulation isn't thicker than that, you're making the problem worse. I mean, in one case, adding asbestos actually cranked up the heat loss by 25%. Crazy, right? And finally, let's talk about things that generate their own heat, like a wire with current running through it. The temperature inside is super predictable. It's going to look like a parabola with the hottest spot right smack in the middle. And that center temperature, it's really sensitive. It shoots up way faster than you'd think if you just make the wire a little bit bigger. It's why even tiny changes can suddenly cause something to overheat. Let's dive into more detail.
All right, let's talk about something you probably see every single day, a simple hot pipe. We're going to follow its story to uncover some pretty wild and honestly kind of counterintuitive ideas in heat transfer. Let's get right into it. I mean, it seems obvious, doesn't it? It's hot on the inside, cool on the outside, so the heat just gets out. But the real story of how that heat escapes is way more interesting. It's not just leaving, it's fighting its way out. So here's the star of our show, a pipe with hot water flowing through it. Now, for the heat to get from that water to the air outside, it can't just teleport. No, it has to go on a journey, an obstacle course, if you will. And this obstacle course has three main parts. The heat has to conquer three totally separate barriers, one right after the other. Each one slows it down. And figuring out these barriers, well, that's the secret to understanding the whole system. So what are these hurdles? Okay, first, the heat has to jump from the moving water to the inside surface of the pipe. That's our first step, convection. Then it has to crawl its way through the solid metal of the pipe wall. That's step 2, conduction. And finally, it has to leap off the outer surface of the pipe into the air around it. And that's convection again. 3 steps, all in a row. Now, this is where it gets really, really interesting. Look at how different these hurdles are. The resistance on the inside and through the pipe itself, they're tiny. You can barely see them. But the resistance on the outside, whoa, it is huge in comparison. It's not just bigger, it's over 400 times bigger than the inside one. It's not even in the same league. In engineering, we have a name for this big guy. We call it the controlling resistance. And that's because it's the main bottleneck. It's the one thing that's really in charge, dictating how fast heat can get out. The other two, they hardly even matter. So here's the key. If you want to make a real change in the heat loss, you have to attack that biggest barrier. Okay, so if we want to stop heat loss, the solution seems pretty straightforward, doesn't it? You just wrap the pipe in some insulation. But this, my friends, is where our story takes a very, very strange turn. You'd think so. I mean, that's what insulation is for. More insulation equals more resistance, which means less heat loss. Simple. But what if I told you that sometimes adding insulation can actually make the pipe lose heat faster? Yeah, you heard me right. This leads us to this kind of mind-bending idea called the critical radius of insulation. See, it's a tug of war. When you add insulation, sure, you're adding a barrier to heat flow, but you're also making the outside of the pipe bigger. You're increasing the surface area, and a bigger surface area can get rid of heat more easily. For small pipes, that second effect can actually win the tug of war. And here's the proof, plain and simple. Look at this. On the left, our bare pipe is losing about 85 watts of heat per meter. But on the right, after we add just the right amount of insulation, that critical amount, the heat loss shoots up to over 105 watts per meter. We added insulation, and the heat just started pouring out. And that's not a small difference. By trying to stop heat loss, we actually cranked it up by a massive 25%. This is one of those classic engineering surprises that you absolutely have to know about. And hey, don't just take my word for it. This is a direct quote from a classic textbook, J.P. Holman's Heat Transfer. It's a real thing. The lesson here is pretty clear. When you're dealing with small pipes or wires, slapping on more insulation isn't always the answer. Okay, let's keep going. We've talked about a pipe that's just kind of passively holding hot water. But what about things that are actually making their own heat from the inside out? So let's swap our pipe for a stainless steel wire. Now it's not just a container anymore. We're going to pass an electric current through it. And because the wire has its own resistance, it starts to generate heat. It basically becomes its own little furnace. So let's kick things off. We're going to push a pretty hefty 200 amps of current through this little 3mm wire. Okay, so that current hits the wire's resistance, and boom, it generates a ton of power, almost 4,000 watts. All that electricity is turning straight into heat. And all that heat has to go somewhere, right? It travels from the inside out, and by the time it gets to the surface, the outer wall is cooking at 215 degrees Celsius. But here's the really important part. Because heat is being created everywhere inside the wire, the heat right at the very center has the longest trip to get out. This causes a kind of temperature traffic jam, making the center the absolute hottest point, reaching almost 232 degrees Celsius. So what's the point of all this? After our journey with this hot pipe and its electric cousin, what are the big ideas? What are the engineering lessons that we should really hang on to? Okay, so what did our pipe teach us? Number one, always hunt down the biggest bottleneck, that controlling resistance, because that's where you can make a real difference. Number two, watch out for that critical radius paradox. It's a huge lesson that our intuition about insulation can sometimes be dead wrong, especially for small things. And finally, when something generates its own heat, remember the center is always the hottest spot. It's a fundamental idea that you'll see everywhere. You know, we started with something incredibly simple, a basic pipe, and from it, we pulled out these powerful principles that apply to everything from cooling your computer to designing a power plant. The basic physics is the same. So the question I'll leave you with is, now that you get it, what are you going to do with it?